Hello, we're going to go through the 2015 practice exam for Math 1229. First question, it gives us two vectors, u and v, and it asks for 3 times u plus 2 times v. So we'll compute that. We'll have 3 times 1, negative 2, 3, plus 2 times 2, 1, minus 1. We can multiply through. So in the first vector, we have 3, negative 6, 9, multiplying each of the entries by 3. In the second vector, we have 4, 2, negative 2, multiplying each entry by the 2 that's in front. Now we can add the components, x plus x, y plus y, z plus z, and we end up with 7. And then negative 6 plus 2 minus 4, and then 9 minus 2, 7. So 7 minus 4, 7. Choice B. Question 2. Find u dot v. Okay, so the dot product, I'm going to write both vectors side by side. 1, negative 2, 3, dotted with 2, 1, minus 1. Dot products involve multiplying the x by the x, the y by the y, and the z by the z, and then adding up each piece. So I'll have 1 multiplied by 2 plus negative 2 multiplied by 1 plus 3 multiplied by negative 1. So add everything up, we get 2 minus 2 minus 3, which is minus 3. So choice D. Okay, question 3, find the cross product. So I'm going to write one particular way of finding the cross product. I'm going to make 2 copies. 1, negative 2, 3, 1, negative 2, 3. 2 copies of the first, 2 copies of the second. 2, 1, minus 1. 2, 1, minus 1. Then I'm going to say the cross product equals, I get rid of the first and last, and my cross product is going to be down products minus up products. So there's going to be 3 entries in there. So first for the down products, I'll have negative 2 times negative 1, that's positive 2. And the next entry will have 3 times 2, that's 6. And then 1 times 1, 1. And then subtract the up products. So for the first up product, I have 1 times 3, 3. And then, let's see, hold on, 3. And then I have negative 1 times 1, so we're subtracting negative 1. And then the last one we have 2 times minus 2, so we're subtracting negative 4. We can simplify. 2 minus 3, negative 1. 6 minus minus 1, 7. 1 minus minus 4, so 1 plus 4, 5, which is choice B. So again, if you're doing a cross product, make 2 copies of the first element of the cross product on the top, side by side, 2 copies of the second element of the cross product down below, cross out the first column and the last column, and then do down products minus up products, and partition it into those 3 components, an x component, a y component, and a z component. Okay, number 4. Which of the following vectors is parallel to the line that goes through the points P and Q? So this could have many answers. We'll try first of all to get the easiest one, P minus Q. Or Q minus P. It could be the reverse. So 2 0, -2, -1, 3, 2. And what we get, the answer may be a multiple of this. So we have to multiply a result by a scalar to make it match. Because multiplying by a scalar leaves it parallel. 2 minus 1, 1. 0 minus 3, -3. -2 minus 2 minus 4. And we look at the options that are there. And can I multiply this by something to make it look like one of these? So if I look at choice B, multiply by -1, I'll make the first entry match, and the second entry will match, but the third entry won't match. If I look at option C, it's completely off. I can't make it match by multiplying. For option D, similar. I can make it close. I can multiply by, let's see, 1, -3 is right, but the -4 is not -5, so it's almost there, but not quite. And then for E, if I multiply everything by -3, I'll get -3, +9, so the first two entries match, and the last entry, I'll get -4 times -3, I'll get +12, not 8. But if I multiply this by 2, I get 2 in the first entry, -6 in the second, -8 in the third, so that's choice A. Okay, number 5. Which one of the following is an equation of the line that goes through the points P and Q? This is a different point P, different point Q. And there's different forms of equations of lines through points. There can be a point parallel form. So a point parallel form is x of t is equal to a point vector P plus t times the direction vector V. So that's point parallel form. And C, E, and D are written that way. It would also be written in two-point form. We're given a point P and a point Q. And that's A. A is written in two-point form, 1 minus t times P plus t times Q. So we could check really quickly. The first point in there looks like P. The second point in there is not Q. So it's not, I wouldn't pick A. It is a form of a line, but it's not matching the data that's given. And for B, 3x plus 2y plus 5z is equal to 6. That's a plane. So that's not even an equation of a line. So you shouldn't even look at B. It's all good. Doesn't match the dimensionality. Okay, let's go about answering this thing. Let's try to find out what the direction vector is first of all. So for direction vector V, I'm going to go from, let's see, from P to Q. And that's Q minus P. So I'm going to take the Q, 3, 2, 5, and subtract the vector, point vector P. 1, -1, 1. Just taking the coordinates and making them components. Then complete the subtraction. 3 minus 1, 2. 2 minus minus 1, so that's 2 plus 1, 3. And then 5 minus 1, 4. So that's our direction vector. 2, 3, 4. And we don't have any of those in D. We have 3, 2, 5. That's not our direction vector. It has a 2, 3, 4, but it's in the wrong spot. That's a point, and a direction vector is multiplied by t. So I'm going to get rid of D. And let's see. Point C, direction vector is wrong. 4, 5, 6. It's not a multiple of 2, 3, 4. So I can just cross that out. All right, and then I can look at the rest of it. Let's look at E. E says the line is given by x equals a point plus t times v. So the v matches, and the point, is it one of the 2 points that's given? Yes, it's point Q. So this was our vector v, and this was our point Q. So it's choice E. Okay, number 6. Which of the following describes a line through the point that is parallel to the line 2x minus 7y is equal to 3? A line given in this form, given in standard form, outputs the normal vector of the line in 2D. And you can have standard form for a line in 3D. It would give you a plane, but in 2D it does give you a line. So a normal vector n, that's the coefficient in front of the x and the y. So the coefficient, the normal vector, the vector that's at 90 degrees is 2 for the x component, -7 for the y component. So that's the normal vector for the line. We want to find an equation of a line that goes through the point 1, 2 and is parallel to this line. So parallel, if we're going to write our line in point parallel form, like all the options that are given, we need to take their normal vector and find a corresponding direction vector. I'm going to draw a diagram. So I'm doing a lot of stuff you don't have to do on your exam to answer these questions. I just want to kind of explain where these ideas come from. So a line L has a direction vector v and it has a normal vector n. Let's say that the normal vector n is a comma b. Then your direction vector v you could create in many different ways, the simplest of which would be to switch a and b. So I'm going to put b here, I'm going to put a here, and then put a minus sign in front of one of them. So you could have b comma negative a or negative b comma positive a. Those would be the two ways that you could create a direction vector from a normal, or vice versa. Given a direction vector, you can create the normal vector in much the same way. Okay, so for this problem, I'm going to do the same thing. I'm going to switch u and v. I'm going to switch a and b. So we have a -7, comma 2, but we have to multiply one of them by a negative sign, and I multiply the -7 by a negative to make it positive. So 7, comma positive 2. So flip them, put a negative in front of 1. So that's our direction vector, and we want to go through the point 1, comma 2. -1, -2. So I'm looking for a is 1, -2 has the point plus 2, 7. So that's wrong because the direction vector is wrong. Direction vector is incorrect. For b, the direction vector is very wrong. They put the point in there. It's not even close. Also, they put the point in this location where the direction vector should go, or they switched the point in C. So another mangling of the formula. And then for D, it has the point that we're asked that the line goes through, 1, -2, plus t times the direction vector v that we found, so it's option D. Okay, number 7. Find a normal form equation of the plane through the point 1, 2, 7, which has a normal given by -5, 2, 8. All the answers are written in the following format: n, point normal form, n dot x minus p, and it has to be equal to 0. N dot x minus p is equal to 0. The option D is thus nonsense, and option E is nonsense. Anyway, so into this we can plug in our normal, which it tells us is -5, 2, 8 dot x minus, I'm not going to write out the x is just x, y, z, and then point P 1, 2, 7 equals 0. So it's a collection of all x, y, z coordinates that satisfy this equation. And if you put them all together, that makes the equation of the plane. Okay. Now, do we have something that matches that? Yes, option A. Okay, number 8. Find a normal for a plane that is parallel to both of these two vectors. So, I'm going to draw a picture. Again, you don't have to draw pictures. I like drawing pictures. There's a plane. So a sheet of paper tilted. So it has, I'll give it a little thickness. Planes are not supposed to have thickness. So just for the purposes of showing the orientation. Okay, then I'm going to put in two vectors. I'll put the vector v, and I put another vector. I'm going to, let's see, I'll put it here. Vector u. Then, for the plane, every plane has a normal vector, n. And the interesting thing is that if the plane contains or is this is not as strict, it's at least parallel to the vectors u and v, then it means that the normal vector for the plane has to be perpendicular to u and v. And there's several ways to construct a vector that's perpendicular to two other vectors, the simplest of which is to use a cross product. So I'm going to say our normal vector n is equal to u cross v, and it could be a multiple of that. It could be the negative of that, or the positive 2 times that, or it could be some multiple of this cross product. Okay, so we're going to use the same process for doing cross product and make two copies of the first one. So 2, 3 minus 1, 2, 3 minus 1, and then two copies of the second one, 0, 1, 4, 0, 1, 4, and then hide the first and last columns, and then construct our cross product as ups minus, or downs minus ups. So for the first one, we have 3 times 4, 12. The second one we have 0. And the third one we have 2. And then subtract the up products. So minus, minus, minus. And then our up products, we have 1 times negative 1, so that's going to be minus 1 that we're subtracting. And then the next one we have 4 times 2, that's 8 we're subtracting. And then 0 times 3, that's 0 that we're subtracting. Now we can clean this up. We have 12 minus minus 1, that's 13. Negative 8, 2. So that's choice B. And if you had have done v cross u, you'd have negative 13, positive 8, negative 2. You'd have to recognize that it would just be the line pointed straight. Straight down instead. Also a normal vector. You could have that line. Okay. Question 9. Find an equation of the hyperplane through the 5-dimensional point with the 5-dimensional normal vector given. So our equation of a plane and a hyperplane is n dot x minus p equals 0, which we can distribute that dot product n dot x minus n dot p equals 0. So n dot x equals n dot p. So that's a way to rearrange the point normal equation for a plane into standard form equation of a plane. And I write down what n is. Normal vector is 3, negative 2, 0, negative 2, 3. And then our x is x1, x2, x3, x4, x5. I'll put a barrier here. Okay, equals, and then n dot p. So our normal dot our point. 1, 0, negative 1, 0, 1, dotted with 3, negative 2, 0, negative 2, 3. Okay, so we're going to have 3x1 minus 2x2 plus 0x3. So anything that has an x3 appear, you can cross out, because it should be 0 times x3. So b and d are gone. So 3x1 minus 2x2 Then we have minus 2x4 plus 3x5 equals, now the right hand side is our dot product, 1.3 plus 0 times 2 plus negative 1 times 0 plus 0 times negative 2 plus 1 times 3. So equals 6. So 3x1 minus 2x2 minus 2x4 plus 3x5 is equal to 6, option E. Notice that option A is equal to 0. Okay. And you didn't have to do that. There's a shortcut to this. If you want to memorize another formula, the shortcut is if you're given a normal vector n and a point vector p, then your standard form equation of that plane would be given by the coefficients in front of the x1, x2, and x3 are going to be the coefficients from the normal vector, 3, negative 2, 0, negative 2, 3. So you put them right directly there. And then the right-hand side is always going to be the dot product between the point and the normal. Okay, number 10. Which of the following equations is or are linear in x, y, and z? Linear means you can't do anything to it except multiply it by a constant. You can't take two variables and multiply them together and result in something that's linear. You can't square them or take the sine or cos or log or exponential of the variable. So multiplication of several variables together, like in option 1, that's not a linear operation. X squared plus y squared plus z squared, squaring a variable is not a linear operation. For the other two, there's nothing weird going on. You're not squaring the x or dividing by y or taking a square root. The second one, or option 4, may not be in the usual form, in the standard form, usual order, but it is in linear. So these are both linear, option 2 and option 4. So choice C. Okay, number 11. Which of the following matrices is not in row reduced echelon form? So we'll go through each one. First one. First column is happy. There's a leading 1, zeros below it. Second column is happy. There's a leading 1 that's down and to the right. And the numbers in its column are 0. So it's happy. Then there's no leading 1 to the bottom right, which is in and of itself is not a problem. We don't need to have one there for this to be row reduced. And up above, because we don't have a leading 1 in the bottom right entry, we can't eliminate the negative 1 and the 3. That's as good as it gets. So it is row reduced. Okay, next one, it's the exact same issue. There's no leading 1 in the bottom right. We can't get rid of the 1 in row 2 or the 1 in row 1 in that third column. Those are going to stay. You can't fix it. You can't make it better. If you can't further row reduce it, then it means it's fully row reduced. Okay, option C, similar in that it doesn't look the way that you want it to look, but it's still row reduced. So in the top left entry, there's a 0 there, and you might say, well, I need that to be a 1. You don't need anything. You can't make it better. There's nothing you can do. There's no row operation that you're capable of performing that will make that 0 in the top left anything except a 0. So it stays that way. Next over, there's a leading 1, and it's in the correct spot. The first leading 1 is at the top. So it's exactly where it's supposed to be. And the 2 beside it, you can't get rid of it. There's no 1 underneath that you could 0 it out with, so it's stuck. It's as good as it gets. Okay, next one over. It's got that nice diagonal of 1s. So that part's good, but then there's a 1 above that last leading 1. And that's the problem. That shouldn't be there. You can further row reduce this. You can take the last leading 1 in the bottom right and then subtract. You can do row 2 gets replaced by row 2 minus row 3. So it's not row reduced. So option D. E is row reduced as well. You have this 2 here. You might say, oh, that shouldn't be there. And why not? You can't get rid of it. There's nothing you can do to eliminate the 2. There's no leading 1 in the positions below it. So can't get rid of it. It's row reduced. Okay. Number 12 and 13 and 14 are all based on this matrix. It has A's in it. It has characters. It has symbols in it. And it wants to know under what conditions does this matrix, augmented matrix, have a unique solution, a one parameter family of solutions, or no solution. Okay. Let's go out of order here. I'm going to look for no solution first. So I'm going to do number 14. No solution means any row that reads 0, 0, 0, not 0. Because that row would state 0x plus 0y plus 0z is equal to whatever's on the right hand side, say 7. And there's no combination of x, y, and z that will make that true. So I want to find a value of a that makes that last row read 0, 0, 0, and then not 0. If I let a equal 2, I'll have 0, 0, and then 1 times 0, which is 0, and the last part, the augmented piece, a minus 1, if I replace a with 2, I'll get a 1 there. So it'll read 0, 0, 0, not 0, if a is equal to 2. So a equals 2 does this. And that's the only value that will do that. Okay, now we'll do 13 rather. 13 says, when do we have a one parameter family of solutions? So this means we're missing, one parameter means missing 1 leading 1. So in order to have a unique solution, every single column has to have a leading 1. And there can't be any rows that read 0, 0, 0, not 0. So missing a leading 1. The bottom right entry in A, the non-augmented part of the matrix, you want to make that a 0. But, so if you make it anything but 0, say you make it a 3, you can turn it into a 1 by dividing by 3. But if you make it a 0, you can't fix it. It's stuck. It's stuck as a 0. But you want to make sure that the entry beside it is not also 0. Sorry, is not non-zero, because that would mean no solution. So you need it to be all zeros on the bottom entry. And that's going to happen when A equals 1. If you use 2, that gives you no solution. If you use 1, you get zeros all the way across. You're missing bottom right leading 1. You have to make that column, that third column, a parameter column, like a t. And that would be your one parameter. So A is equal to 1. Okay, now we'll jump to number 12. For what values of A does the system of equations have a unique solution? So unique would be one where you have x is equal to number, y is equal to number, z is equal to number. And that's going to happen when you have 3 leading 1s in your row-reduced matrix. And that will always be possible if you pick any value of A except 1 or 2. For example, if you pick 3, in the bottom entry you'll have 3 minus 1, so 2 times 3 minus 2, so you'll have 2 in the bottom, and then the entry beside it you'll have 2 as well. Then you could take row 2 and divide it by 2, get a leading 1, and then 0 out the negative 3 and the 4 above it. And then you can have x is equal to something, y is something, z is something. If you pick 4 for A, you can do the same thing. 7 for A, same. Negative 8 for A, the same. You can always divide it by whatever number is there, get a leading 1, 0 the numbers above it, get the identity matrix, bar, whatever the right-hand side simplifies to, and upon row reducing. So the answer here is, as long as that bottom entry that in the third column is not 0, you can row reduce this to the identity on the left-hand side. And the things that make that entry 0 would be a is equal to 1 and a is equal to 2. So if we exclude those, any value of a such that a is not equal to 1 and a is not equal to 2, then we're guaranteed a unique solution. That last one, number 12, is a bit confusing. Yeah, so you can go over that part again, listen again, and think about it a little bit. Okay, 15. It's asking for the 2, 3 entry of the matrix A. So 2, 3 entry. I'm not sure if you need the brackets around the 2, 3, doesn't matter. 2, 3 entry, which means we're going to take the 2, 3 entry of the first matrix and add it to 2, 3 entry of the second matrix it would get by completing the matrix multiplication and then multiplying everything by 3. So the 2, 3 means row 2, column 3. So we're looking for that bottom right entry. I have to calculate the corresponding bottom right entry of the matrix multiplication on the right hand side. You could, if you really want, you could perform the entire matrix multiplication. Do all the dot products. Please don't. Do this instead. To get the 2, 3 entry of the resulting multiplication, I'm going to take row 2 and dot it with column 3. If you wanted the 1, say you wanted the 1, 2 entry, then you would take row 1 and dot it with column 2. Here we go. So we're going to have A23 is equal to 2 plus 3 times that dot product. 1, negative 1, 0, 2, dotted with 1, negative 3, 1. So that's 2 plus 3 times negative 1 times 1. 0 times negative 3, 0. 2 times 1, 2. So that's going to be 2 plus 3 times 1, which is 5. So option E. So I check something. Okay. Yeah. Okay, number 16. Let A equal this matrix with a K in it. Don't be afraid of K. Don't be afraid of A's and B's and K's and C's. And let capital I be the 2 by 2 identity matrix. Find the value of K for which A squared is equal to I. A squared means A multiplied by A. So I'm going to write that 102K multiplied by 102K. And we want this equal to the identity matrix, which is 1001 for 2 by 2. Now let's do the multiplication. On the left, we're going to have first row dotted with first column. So 1 times 1 plus 0 times 2, we'll have 1. Now for the right entry, we're going to take first row, second column. So 1 times 0 plus 0 times k, so 0. Then bottom left, we're going to have second row times first column, so 2 plus 2k. And then last, we're going to have 2 times 0, 0 plus k times k, k squared. And we need that to equal 1001. So we have two requirements. We need 2 plus 2k to equal 0, the bottom left to equal the bottom left. That means that 2k is equal to negative 2, subtract 2 from both sides, which means k is equal to negative 2 over 2, which is negative 1. We also need the bottom right to equal the bottom right. So k squared is equal to 1. And that tells us that k is equal to positive 1 or k is equal to negative 1. And we need both things to be true simultaneously, and the only value of k that makes both things true at the same time is k is equal to negative 1. So choice B. Okay. 17. We're given the inverse of a matrix that in the original matrix, A is filled with letters. And then we're asked to find the value of x2. So that's the y value. In the unique solution to the system of linear equations, written in a really bizarre way, this is a classic question. You have to expect this type. It's kind of one of the, I don't want to say it's the only reason, but it's one of the main reasons why you learn how to find an inverse. Because if you find the inverse, then your solution, x, to your system of linear equations is x is equal to a inverse times b. This system of equations you could rewrite as ax is equal to b, where b is 4, 7, 3, the right-hand column. Okay. So I'm going to write this out in a slightly different way again. Our vector x is x, comma y, comma z, which you could write as x1, x2, and x3 if you want. And then that's equal to a inverse, 1, 0, negative 2, 3, negative 1, 1, 2, negative 3, 2, and then multiplied by b, 4, 7, 3. Now we only want y. We only want this one. So I'm going to take row 2 and then dot that with that column. And that will give me the y value. If I want the x value, I'll take row 1, dot the column. If I want the z value, I'll take row 3, dot the column. So then y is going to be equal to 3 times 4, 12, negative 1 times 7, minus 7, and then 1 times 3, positive 3, and so negative 7 plus 3, negative 4, 12 minus 4, 8. So option D. And then we'll take a break. The rest of it will be covered in the next video. Okay, number 18. One moment. Okay, number 18. It says determine the rank of the matrix. To determine the rank, you have to row reduce. So my first step in row reducing is I'm going to use this leading 1. I'm going to use it to zero out the 3 that's underneath. So my move is I'm going to replace row 2 with row 2 minus 3 times row 1. I'll leave everything else the same. So 1, 0, 1, 2, didn't change that. Then second row, 3 minus 3 times 1, 0. Negative 1 minus 3 times 0, negative 1. 2 minus 3 times 1, negative 1. And 9 minus 3 times 2, so 9 minus 6, 3. And the second row doesn't change. The third row doesn't change. 0, 1, 1, negative 3. All right, next. Next step is I'm going to replace, no, I should multiply row 2 by negative 1, but I'm going to go a little bit of a sequence, a usual order of doing things, and replace row 3 with row 3 plus row 2. So row 1 stays the same, 1, 0, 1, 2. And then we have 0, negative 1, negative 1, 3, and then 0, 0, 0, 0. Just add row 2 and row 3 together and get 0 because there are negatives of each other. And then there's one more step we can do. That's take row 2 and multiply by negative 1 to fully row reduce it. 1, 0, 1, 2, 0, 1, 1, 3, 0, 0, 0, 0. That's fully row reduced. We have a leading 1, 2 leading 1s there, and then we can't possibly get a leading 1 in the next entry. So if we row reduced, now to get the rank, we count how many leading 1s, and we find that there's 2 leading 1s. Or you can count the number of non-zero rows, and there's 2 non-zero rows. Whatever the case, they're going to agree. So that means rank 2. Number of leading 1s will equal to the number of non-zero rows. I like to think of them leading 1s though. So rank 2, option C. Okay, number 19. Each of the following statements is true. Every linear system with 7 equations and 7 unknowns has infinitely many solutions. False, because there can be a row. So one of those equations, one row, could be 0, 0, 0, 0. It's 5, 6, 7 unknowns, and then not 0. We could have that. So it can't be option 1. That can't be true. Option 2, every linear system of 7 equations and 5 unknowns has infinitely many solutions. It's the same. It also can't be true because it could be no solution. Same thing. If you get one of those equations, could be 0, 0, 0, not 0. Okay, next. Every linear system of 5 equations and 7 unknowns has infinite many solutions. Again, we have this problem. No solution could happen. We could have a row that's all zeros and then the right hand side that's not 0. Because it doesn't say homogeneous. That's the next one. Option 4. It says every homogeneous. Homogeneous means the right hand side is all zeros. Right hand column of augmented matrix is 0. And that means we cannot have 0, 0, 0, not 0. That means it's impossible to have no solution. We're either going to have a family or unique. And if it's unique, it'll be the trivial solution. Okay, for option 4, it says 5 equations and 7 unknowns. That means we can't have a leading 1 for every one of the unknowns. We're going to be missing at least 2 leading 1s. That guarantees, because we've eliminated the possibility of having no solution, the absence of 2 leading 1s means we're going to have 2 parameters. So that's a family of solutions, an infinite number of solutions. So 4 is definitely true. But just to be safe, every homogeneous system with 7 equations and 5 unknowns, well, you could have, for 7 equations and 5 unknowns, there's enough equations to give a leading 1 to each of the unknowns. So we could have a unique solution, or we could have a family, but it's no guarantee. We can't guarantee that every single one of the homogeneous systems of equations with 7 equations and 5 unknowns has infinitely many solutions. So no guarantee means I can't circle it, because it says must be true. So that was option 4. Okay, number 20. Coefficient matrix of homogeneous system of 7 equations, 11 unknowns has rank 5. Okay, how many parameters are there in the family of solutions? Rank 5 means 5 leading ones. 11 unknowns. So we have 11 unknowns, 11 variables, and 5 leading ones. That means that we have 6 columns are missing a leading one. 11 minus 5. That means 6 parameter family. And notice that the fact that there are 7 equations does not factor into this. It doesn't matter how many equations there are. It's how many unknowns do you have and what's the rank. So option A. You're thinking about taking a row-reduced matrix, looking at its columns and saying how many leading ones, which columns are missing a leading one. Every column that's missing a leading one gets a parameter. Well, you only have 5 leading ones to go around because the rank is 5. There's 11 possible spots you could put those leading ones. That means there's 6 spots that will not have leading ones. That means there's 6 parameters in the family of solutions. Okay, number 21. Consider a system AX is equal to B, where A is 10 by 10 and invertible. Invertible, that's important. That's probably the key to this. Which of the following statements is false? Rank of A is 10. That's definitely true. And here's why. The fact that the matrix A is invertible means you can write A bar identity and row reduce it to identity bar A inverse. And if you can row reduce in this way, then that means that the row reduce echelon form of A is identity. And if that's the case, then when you row reduce A, you get a 10 by 10 identity matrix, which means 10 leading ones, which means a rank of 10. So A is true. B, the rank of A joined with B is also 10. Adding something cannot decrease the rank. It can increase it. However, you have a 10 by 10 system that already has a rank of 10. Adding on another column cannot increase the rank. You can't introduce leading ones by adding another column. So it's true. It's 10. It's going to stay exactly the same. C, the system must have infinitely many solutions. That one's the false one. It's false because if the matrix is invertible, then X is equal to A inverse times B gives unique solution. Not a family of solutions. So the answer is C. And then for fun, D, row reduced echelon form of A is identity matrix. Well, I use that to infer that A is correct. Since A is invertible, you can put it into this A bar identity and then row reduce it to identity bar A inverse, and that means that the A has to be able to row reduce to the identity. So D is true. Okay. Number 22. For number 22, I think it's imagined that you will do a cofactor expansion. Please do so if you like. If you do a cofactor expansion to get the determinant, I'd expand along column 1. It has a lot of zeros in it. I'm going to do it a different way. I use the secret method. Maybe you've seen it before, maybe you haven't. But the secret method is as follows. I can make 2 copies of the matrix side by side. So 0, 2, 4, 1, 13, 26, 0, 4, 16. That's copy 1, and then directly beside it, 0, 2, 4. When you do this, it is helpful to make them equidistant. Make the space between the entries approximately the same. the steps line up better. Okay, and then you can hide the last one only. And then your determinant is going to be determinant of A is going to be down products minus up products. So here's your down products. Your down products are 0 times 13 times 16, which is 0, plus 2 times 26 times 0, which is 0, and then 4 times 1 times 4, which is 16. Now your up products, we have 0 times 13 times 4, which is 0, 4 times 26 times 0, which is 0, thank goodness for those zeros, and then 16 times 1 times 2 plus 32. And then we can simplify this. We have 16 minus 32, which is negative 16. Option C. Okay. I think it's called basket weaving, the basket weaving method. Okay. Number 23. It says to find the determinant of negative 3 multiplied by I to the power of 3, where I is the identity matrix of order 27. So I'm going to just imagine 3 by 3. Or 4 by 4. We'll do 4 by 4. So first part is no matter what dimension I has, like I squared, that's identity times identity is going to give you identity, multiplied by identity again, I to the 3, that's also going to give you identity, etc. So I to the power of 3 is just I. Then negative 3i, if I is 4 by 4, that's going to be negative 3 multiplied by 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, which, put the negative 3 in, negative 3, 0, 0, 0, 0, negative 3, 0, 0, 0, 0, negative 3, 0, 0, 0, 0, negative 3. Then we take the determinant of that, and it's triangular, upward and lower triangular, or diagonal. So we would multiply the negative 3's by each other. We have negative 3 multiplied by itself 4 times, so negative 3 to the power of 4. If it was 27, so order 27 means 27 by 27, we will have negative 3 multiplied by itself 27 times. Now 27 is an odd number, so it's going to end up with a negative sign, negative, and then 3 to the 27. So choice C. And if it was order 26 instead, we would have positive 3 to the power of 26, because a negative power, a negative number raised to an even power, an even number, will become positive. Like negative 3 squared gives you positive 9. Negative 3 to the 4 gives you positive 81, and so on. Okay, number 24. Let A be a 2 by 2 matrix with determinant 4. Find the determinant of 3 times A transpose. Okay, so I have a determinant of 3 times A transpose. And we have a determinant property. We the determinant of two matrices A times B is the determinant of A multiplied by the determinant of B. And we have another property. We'll use that one first. So determinant of, I'll put the 3 and the A together, so determinant of 3A times the determinant of A transpose. So we'll do that. Then determinant of A transpose. Transposing does not change the determinant, so determinant of A transpose is just the determinant of A. So this can be rewritten as determinant of 3A times the determinant of just A. Next, multiplying a matrix by A, or multiplying a matrix by 3, means you're multiplying each row by 3. And one of our shortcuts for calculating determinants allows us to common factor a constant out of any row and or any column. So I'm going to take the 3 out of row 1 and out of row 2. This is a 2 by 2 matrix, so it takes it out of all the rows. So I'm taking first the 3 out of row 1, so a 3 comes out. Then out of row 2, so another 3 comes out. And then we have determinant of A times determinant of A. And again, that was, we took the 3 out twice because it's 2 rows. Out of row 1 and out of row 2. Now we can finish this. That's 9 multiplied by determinant of A is 4. And determinant of A is 4. So we have 12 times 12, so 9, 3, 3, so 12, 12, 144. So 24 is E. Okay. Now for 25. '25 is another kind of a cute question. And do it over here. It's asking us to find the determinant of A plus A times A inverse for the given matrix A. I'm going to clean up what's inside that expression first. Determinant of A plus A times A inverse. Well, no matter what A is, A times A inverse is the identity matrix. So we have A plus I. So I'm going to now fill in the blanks. I'm going to put what A is. A is 2, 2, 3, 0, negative 1, negative 2, 0, 1, negative 1. And then we're going to add the identity matrix to that. 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's the determinant of. Now we add entry by entry. So 3, 2, 3, and then 0, 0, negative 2, and then 0, 1, 0. Okay, it's not quite triangular. So I'm going to do a row swap. I'm going to swap row 2 and row 3. Now when we do that, we pick up a minus sign. Any swapping a row inside or a column in a determinant introduces a minus sign in front. So determinant of, I'll drop with the extra bracket, 3, 2, 3, 0, 1, 0, 0, 0, negative 2. And now we can take the determinant. using a shortcut that it's upper triangular form. And the determinant of upper triangular form is the product of the diagonal. I guess I should say main diagonal. So that's negative. We have 3 times 1 times negative 2, which is positive 6. So option E. Okay. Number 26. 26 is another one of those matrices that's filled with letters. We have the determinant A, B, C, D, E, F, G, H, I is equal to 3. It's asking for what happens if it's multiplied by some constants in there. So we're going to do a few things. We're going to do a factoring, common factoring, out from, let's do row 1 first. Out of row 1, I'm going to take a 3 out. So out comes the 3 from row 1. Only row 1, not doing anything else. Not yet. And then determinant is A, 3B, C. So I divided each of the entries by 3. Put the 3 out front. D, this did not change. It did not change row 2, only changed row 1. Okay, now we're going to do it again. This time we're going to common factor a 3 out of column 2. So we have a 3 times a 3 times the determinant of, almost there, A, B, C, D, E, F, G, H, I. And this says, we have that, determinant of that thing is 3, so 3 times 3 times 3, we get 27. So option A. Next one. So I want to, again, relate this matrix in 27 to the original matrix, A, B, C, D, E, F, G, H, I. And I'm going to do that by using a sequence of elementary row operations and tracking, when necessary, how that changes the value of the determinant. To make it look more similar, I'm going to replace, I don't want, see that 3A, 3B, 3C, I don't want those there. So I'm going to take row 2 and replace it by row 2 minus 3 times row 1. And that's a free move. That elementary row operation does not change the determinant. Swapping a row or swapping a column introduces a minus sign. Common factoring brings a number out front. And doing this operation, replacing a row with itself plus or minus a multiple of another row, does not change the determinant. Alright, so we have the top row stays the same, we didn't do anything. Then row 2, we had 3A minus D and then minus 3A, so that's negative D. And the same thing happens, negative E, negative F, and then GHI. Now I'm going to common factor out a minus sign. Common factoring out negative 1 from row 2. So we have negative determinant of A, B, C, D, E, F, G, H, I. Well, that's our original matrix, so we have negative, and the determinant of our original matrix is 3, so minus 3. Option B. Okay, 28. Okay, we're out of that into something different. We're given the matrix A and asked to find the determinant of A inverse. And luckily, there's a shortcut. We do not have to find the inverse of A and then take its determinant. You're welcome to do that. I think you're going to get fractions, a fraction nightmare. Really bad fractions. Anyways, determinant of A inverse is 1 over the determinant of A. It's a glorious property. Let's find determinant of A. Determinant of A, it's triangular. So the determinant is the product of the main diagonal. 9 times 2 times 1, we get 18. So that means our determinant is 1 over 18. Determinant of A inverse, I mean. Okay, so option C. Okay, number 29, asking for the minor, the 2, 1 minor of A. So that's going to be the determinant of the submatrix A, 2, 1. So we take row 2, column 1, cross them out. That's how you create the submatrix A21, and then take the determinant of that submatrix. So determinant of 2, 2, 0, 3. And for a 2 by 2 matrix, we have a nice formula for determinants. It's down products minus up products. So that's going to be 2 times 3 minus 0 times 2. So 6 minus 0, which is 6. So option A. Now, cofactors are a little bit different. There's an extra piece in front. It's the minor multiplied by negative 1 to the power of 2 plus 3. So negative 1 to the power of 2 plus 3 times the determinant of the submatrix A23. So cross out row 2, and this time column 3. So we have negative 1 to the 2 plus 3, so negative 1 to the 5, multiplied by a different 2 by 2 determinant. We're going to have 3, 0, 1, 1. And we use the same formula, down product minus up products. Negative 1 to the 5 is negative 1, so this 5 is odd, and then multiplied by 3 times 1 minus 1 times 0. So negative 1 multiplied by 3 minus 0. Oh, sorry, that's a plus 3 now, minus 3. 3 minus 0, so negative 3. Option D. All right. Number 31. Find the value of k for which the matrix has no inverse. Matrices with a determinant of 0 have no inverse. I don't know if it's a hack, but it's a fast way to do this. No inverse when determinant of A equals 0. So I'm going to force this to happen by taking the determinant of A, setting it equal to 0, and solving for k. So our 2 by 2 determinant, k times negative 5, and then minus 3 times 7. And we want that to be 0, and that would cause no inverse. So we have minus 5k minus 21 equals 0. Minus 5k is equal to positive 21. Add 21 on both sides. Now divide both sides by minus 5. So k is 21 over minus 5. So choice B. The minus can go in front of all of it, on the bottom or on the top. They're all the same. Okay, 32. Find the value of k for which this matrix has no inverse. Same. Just a harder determinant. No inverse. There's other ways too. You could, let's see, it might be easier to reduce this. and then make a row of zeros, but no, let's just do it this way. No inverse when determinant of A equals 0. So I'm going to use that secret method, the basket weaving method, to take the determinant, make 2 copies side by side. Two, 1, minus 1, k, 2, minus 2, 0, 3, 1, and 2, 1, minus 1, k, 2, minus 2, 0, 3, 1. Hide the last one, the last column, and then our determinant is going to be down products minus up products. So our down products, 2 times 2 times 1, we get 2. And then 1 times negative 2 times 0, we get 0. And then negative 1 times k times 3, we get negative 3k. Now for the up products, we have 0 times 2 times negative 1, which is 0. 3 times negative 2 times 2, so that's negative 12. And then 1 times k times 1, that's plus k. And we want to sabotage the process of creating an inverse, so we want to create, or we want to make sure that this determinant is equal to 0. So I'm going to set it equal to 0 and find the value of k that makes this come true. Now simplify. So 2 minus 3k. Next, lots of mistakes can happen when you're not careful with this next thing. Is this negative sign is multiplied by everything inside this second bracket. So we have negative, negative 12, that's plus 12, and then minus k. Equals 0. Oh, I screwed something up. 2 times 2 times 1 is not 2, it's 4. So sorry about that. Just looking ahead, saying my answer wasn't making any sense. Okay. Now, 4 plus 12, 16. Negative 3k minus k minus 4k equals 0. Add 4k to both sides. 16 equals 4k. Then divide both sides by 4. So k is 16 over 4, which is positive 4. So option C, number 32. Okay. Number 33. System of linear equations, ax equals b has 3 equations and 3 unknowns with determinant a equals 0. Which of the following statements is true? A. The system never has a solution. B. The system always has at least one solution. C. The system always has a parametric family of solutions. D. The system never has a unique solution. And the answer here is D. I'll tell you why. If the determinant of A equals 0, then A inverse does not exist. So we cannot write our solution x equals A inverse times B. And any square system, so n by n, same rows, same columns, with a unique solution has to be able to be solved this way, using the method of inverses. Another way to look at this is that if the determinant is 0, then the matrix A does not row reduce to the identity matrix. Because if it did, then the inverse would be able to exist. Oh, and by the way, the reason I can say that the matrix is square is because it says it has 3 equations and 3 unknowns, so we don't have to worry about anything weird happening. So if it doesn't row reduce to the identity matrix, so going back to that idea, then it means that it's missing some leading ones. So that lack of full rank means you're either going to have parameters or you're going to have no solution. So it's going to be a family of solutions or it'll be no solution. That can't be a unique solution. Okay, number 34. If A is a 9 by 9 matrix with determinant A equals 5, which of the following statements must be true? A is invertible. Yes, since the determinant of A is not 0. Two, for any 9 by 1 column vector B, the system AX equals B has a unique solution. Also true. And that's because if the inverse exists, you can write it as X equals A inverse times B using the method of inverses. Then for 3, the row reduced echelon form of A is the identity matrix of order 9. Also true, since A inverse exists. And again, the connection is we can create the inverse another way. We could start A bar identity and row reduce it until it's identity bar A inverse. And if you can do that, then that means that A has to row reduce to the identity matrix. And this is a 9 by 9 system, so that means it'll be an identity matrix that's also 9 by 9, which means order 9. So true as well. So it's option E. All of them are true. And 35. Another classic. If it is known that the determinant of this matrix that's filled with letters is equal to 3, find x2 in the solution to the system of equations shown below. So this matrix system you could write as AX equals B. So our right hand column B is 4, -8, but we're not going to do this using the method of inverses. We're going to use something called Cramer's rule. It would have been the last topic you covered in class. And it says that x, your solution to your system, the x value of your solution to your system of equations will be given by the determinant of the replacement matrix A1 divided by the determinant of A, and y is equal to the determinant of the replacement matrix A2 divided by the determinant of A. Now, I'm going to write down A again. A, matrix A is 2 little a, 1 little b. And then the replacement matrix, A1. Replacement matrix means replace the first column with B. So I'll have 4, -8, AB. And then A2 means replace column 2 with B. So I'll have 2, 1, and then 4, -8. Now, this question is asking for x2. That's the y value. So we're tasked with calculating this quantity, determinant of replacement matrix A2 divided by the determinant of A. We're told that the determinant of A is 3. So equals 3. Oh, sorry, 3 goes down below. The denominator is 3. So that's the determinant of A downstairs. Now we need the determinant of A2. Our replacement matrix A2. And that's down products minus up products. So 2 times negative 8, negative 16, minus 4, we get negative 20. So we get negative 20 over 3, which is option A. It does not have to be a pretty number. Okay, and then we'll look at part B of the exam. I think that's the last question, last multiple choice. Look at part B in the next video. Okay, number 36 on the 2015 final exam for Math 1229. Number 36 asks to find the distance from the point to the plane. And the formula for distance between a point and a plane D is equal to the absolute value of the normal vector of the plane dot Q minus P divided by the length of the normal vector. Where Q is the point in question, and P is any point in the plane. So if you want, you could get a point on the plane by choosing an x value, choosing a y value, and getting the resulting z value. So to get the point, I'm going to let x equal 0, y equal to 0, and then find z. So we have 3 times 0 minus 0 plus z is equal to 1. That means z is equal to 1. So our point, P, is equal to 0, 0, 1. Now, I'm going to write down our ingredients. Q is 1, negative 1, 2. And then n, normal vector. We get the normal vector for the plane by stripping out the coefficients in the normal form expression for the plane. So the x coefficient, 3, comma the y coefficient, minus 1, and the coefficient in front of z, positive 1. 1 times z there. Now, we didn't really need to get the point P. We could have distributed this dot product as n dot Q minus n dot P, and then n dot P would give us 1, the right-hand side of the expression for the equation of the plane. So that'll always give you the D, or the C, whatever that constant is on the right-hand side. We'll see that anyway. Or no, we won't, because we're going to subtract out the points and just get Q minus P first. Okay, so let's finish getting the ingredients we need. So we're going to get Q minus P. And if in your formula you may have P minus Q, or have the labels flipped, but it doesn't matter. The absolute value sign takes care of that. Don't get caught up on that stuff. So we have 1, negative 1, 2, minus 0, 0, 1. So 1 minus 0 is 1, negative 1 minus 0, negative 1, 2 minus 1, 1. Now we're also going to need the length of n, magnitude of the normal vector. So that's the square root of the sum of the component, the square root of the sum of the components squared. So 3 squared plus negative 1 squared plus positive 1 squared. So that's going to be 9 plus 1 plus 1, all inside a square root, so that's the square root of 11. And the square root of 11 does not root nicely, so it's just going to stay that way. Okay, now plug everything in. So we have a normal vector, 3 3, negative 1, 1, dotted with q minus p, which I just calculated as 1, negative 1, 1. And absolute values divided by square root of 11. Now complete the dot product. 3 times 1, 3. Negative 1 times negative 1, plus 1. And 1 times 1 plus 1, all over the square root of 11. So that's the absolute value of 5 over square root of 11, and the absolute value of 5 is just 5 since it's a positive number. Now, if we had have done it reversed, if we had p minus q, we would get from the dot product would have minus 5. No, we wouldn't. Yes, we would. We have minus 5 from the dot product if we had q and p flipped. But when we take the absolute value, we'd end up with a positive anyway. Okay. And the shortcut, if you wanted to use a shortcut, is up at the very beginning, distribute that dot product. So you have n dot q minus n dot p over magnitude of n. And then that's n dot q minus 1 over magnitude of n. Where this 1 here comes from here, that one that's there. So if the right hand side was something else, if it was 3, there'd be a 3 there. That's what will always happen. When you take the dot product of a point P that's on this plane with the normal vector of the plane, you will get the right hand side. Okay. Number 37, find the point of intersection of the line with the plane. The easiest way to do this is to start by writing the line in parametric form. X is equal to 1 plus 2t, y is equal to 0 plus 4t, and z is equal to 3 minus 2t. Now, what a point of intersection means is that the line and the plane share the same x, y, z coordinate. So I can use the x coordinate, or the expression that describes the x coordinate for the line, in the x coordinate for the plane, and the same for the y and for the z. I'm just going to rewrite it. X minus y plus 2z is equal to negative 5, and then replace as I go. So x gets replaced by 1 plus 2t. If they intersect, then they're going to have the same coordinate, so that's why I'm substituting them in. Minus y, so minus 4t, plus 2 times z, 2 times 3 minus 2t, equals minus 5. And I'm going to put brackets around the 3 minus 2t, just to make sure that I multiply both of those terms in the z piece by the 2 that's in front. Okay, now I'll clean up a little bit. 1 plus 2t minus 4t plus 2 times 3, 6, and then 2 times negative 2t minus 4t equals minus 5. Now clean up. We have, first add the constants together. 1 plus 6, we have a 7 on this side, and then add the t stuff. 2t minus 4t, that's negative 2t minus 4t, negative 6t equals minus 5. Then, let's see, I'm going to add 6t to both sides. So 7 is equal to negative 5 plus 6t. Then add 5 to both sides. So 7 plus 5 is equal to 6t. So 12 is equal to 6 times t. So t is equal to 12 over 6, which means t equals 2. That's not the answer. You cannot stop here. That's just telling you the value of t inside your point parallel equation of the line that gives you the point of intersection. Now we're actually going to find the point of intersection. We're going to find x, y, z coordinate using the parametric form. X is equal to 1 plus 2 times t. We found t is 2, so 1 plus 2 times 2. 1 plus 4, we get 5. Now y is equal to 0 plus 4 times t. So that's 0 plus 4 times 2, which is 8. And then the last one, z is equal to 3 minus 2t. That's 3 minus 2 times 2. 3 minus 4, negative 1. So our point of intersection is 5, not very good, 5, 8, negative 1. Okay. Number 38. We're given two matrices, A and B. We're asked to find the determinant of A times B. You can do this one the easy way, you can do this one the hard way. The hard way is to multiply A times B first, and then take the determinant. A lot of work. Because if you do it the easy way, you use the determinant property. Determinant of A times B is the determinant of A times determinant of B. Just a comment here. Not part of this question, but I'll mention it because it's sometimes something that's done in other questions. The determinant of A plus B has no shortcut. It is not determinant of A plus determinant of B. You can't do that. So that's just an aside. We're not using that here. We're not asked to add two matrices together and take their determinant. We're asked to multiply them, take the determinant. And we do have a property for that. So we can distribute the determinant operation to A and B. Alright, now what makes that so nice is that A is upper triangular and B is lower triangular. And the determinant of triangular matrices is just the product of the main diagonal. So for the first one, for A, we multiply the 2 times the 4 times the negative 1. So 2 times 4 times negative 1. That's for the first matrix. And then for the second matrix, it's upper triangular. So 2 times 1, or so 3 times 2 times 1. And then we can clean that up. That's negative 8 from the first one. And then 6 from the second one, which is negative 48. Okay, number 39. We're asked to find the determinant of a 3 by 3 matrix. Well, the format of this would invite many different ways of calculation. 3 by 3s, we could use basket weaving. But then, when you do that, you're stuck with multiplying 11 times 22 times 33. And doing those types of multiplications several times, 6 times to be precise. A lot of work. And I highly recommend that you don't solve it that way. Although I think that this year I did mark a few that did it that way and got it right. Must have taken half an hour or more to do, unless they're really fast at multiplying. Anyway, other things you can do, other ways of calculating the determinant. You could look for duplicate rows and duplicate columns, because if you find that one of the rows is a duplicate of another row, or one of the columns is a duplicate of another column, or a scalar multiple of another column, or a scalar multiple of another row, then that means that the determinant is 0. But we don't have that. Multiply the first row by something, I'm not going to get the second or the third. Multiply the first column by something, I'm not going to get the second or the third. Look at the second row, I can't multiply it by anything to make one of the other rows. Look at the second column, same. So that exhausts that avenue, hoping to find the determinant is equal to 0 by looking at duplicate rows, or scalar multiple rows, or scalar multiple or duplicate columns. Next, we can look at elementary row operations. So I'll try that. Simplify using row operations. We can swap any two rows or columns. And that picks up a minus sign on the determinant. So I'm going to write this down. Determinant of 11 21, 31, 12, 22, 32, 13, 23, 33. So we could do a swap, pick the minus sign in front, or we could common factor. We could factor a constant out of any row or any column. That constant would go in front of the determinant. Or a move that doesn't change anything, I could take one row or one column and subtract it from another row or column in any multiple. So that's what I'm going to do next. My move will be, I'm going to take row 2 and replace it by row 2 minus row 1. Let's see what happens. Leave row 1 alone. 11, 21, 31. Now subtract row 2 minus row 1. 12 minus 11, 1. 22 minus 21, 1. 32 minus 31, 1. Okay, I'm going to do the same thing for row 3. I'm going to replace row 3 with row 3 minus row 1. Let's see what happens. 13 minus 11, 2. 23 minus 21, 2. 33 minus 31, 2. Okay, now we can see that row 3 and row 2 are multiples of each other. That means the determinant is 0, but I'll go one more because I know everyone likes to see the duplicate rows, duplicate columns, so I'll do another move. I'm going to replace, or even better, I'm going to replace row 3 with row 3 minus 2 times row 2. Let's see what happens. 11, 21, 31, 1, 1, 1, and then 2 minus 2 times 1, 0, 2 minus 2, 0, 2 minus 2, 0. So we have a row of zeros. That means determinant of A equals 0. Okay, number 40 asks us to find only the 2, 3 entry of the adjoint of A. So my process for doing this is, let's see, do I want to take the transpose first or the transpose later? Let's do transpose first. So step 1, A transpose equals, so the first row becomes the first column, 2, 3, negative 2. The second row becomes the second column, 0, 1, 3. Third row becomes the third column, 0, 0, 1. Next, we calculate the matrix of cofactors of the transpose. Matrix of cofactors of A transpose. So we'll have, when we do that, our cofactors have the negative 1 to the I plus j, negative 1 to the power of the row plus the column. And that results in the following plus minus pattern. Plus, minus, plus, minus, plus, minus, plus, minus, plus. And then we get minor M11, M12, M13, M21, M22, M23, M31, M32, M33. Now we want only one of these entries. We don't want all of them, just one. We just want the 2, 3 entry. So that's row 2, column 3. So here's row 2, there's column 3. We're looking for this entry here. So I want minus M2 2, 3. So here's the matrix. I'm going to rewrite it. A equals 2, 3, negative 2, 0, 1, 3, 0, 0. Oh, I don't want A, I want A transpose. Copying the wrong thing. Back when I took this course as an undergraduate, this was one of the mistakes that I made on my exam. I got the transpose of the matrix, and then when I went to make a copy of it to make the minor matrix, I duplicated A instead of A transpose. So I just tried to do it again. So 2, 0, 0, 3, 1, 0, negative 2, 3, 1. There. Now I want to make, let's say transpose, not A. Now I want to get the 2, 3 minor. So I'm going to cross out row 2, column 3, and then take the determinant of what's left. Determinant of 2, 0, negative 2, 3. And then that's down products minus up products. So 2 times 3 minus negative 2 times 0. So 6 minus 0 equals 6. And that goes here for M. That's M23. And then leave the blanks in. We just need the one number. We have a minus in front, and then we found that it's a 6. Oh, wrong color. Minus 6. We don't need the rest of the entries. So I'll say answer. Oh, stop. Answer is negative 6. The person marking it knows exactly what you think the answer is. They don't think it's 6, and they don't think it's A transpose or M23. Okay, number part B. Without finding the rest of the matrix, adjoint of A, find determinant of the adjoint of A. Well, that's actually a very kind instruction. Not that finding adjoints is particularly challenging, it's tedious. You do the same thing that was just done for that one point. You do that same thing 8 more times, and you got the adjoint. Here's the trick for finding the determinant of the adjoint without actually finding the adjoint. To use this trick, we have to know a formula for the inverse in terms of the adjoint. A inverse is equal to 1 over the determinant of A multiplied by the adjoint of A. Now to proceed, we're going to need to find the determinant of A. So let's do that right now. For A, scroll up, too far. So what do we got here? Okay, so we got 2, 3, negative 2, 0, 1, 3, 0, 0, 1. And this is an upper triangular matrix. So the determinant is just the product of the main diagonal again. We don't need to do anything fancy. That's 2 times 1 times 1, so we get 2. Well, I'm going to take that 2 and plug it in down here for determinant of A. So A inverse is equal to 1 over 2 times the adjoint of A. I'm going to rearrange, multiply both sides by 2. So So 2A inverse is equal to the adjoint of A. Next is we're going to do something to both sides of this equation. The thing that we're going to do is we're going to take the determinant. Determinant, take the determinant of both sides. So determinant of 2A inverse equals determinant of the adjoint of A. Now A is 3 by 3. And that means A has 3 rows. So I'm going to common factor out this 2 from each of the rows. When you multiply a matrix by a constant, you can think of that as multiplying each row by that constant. So there's a 2 multiplied by row 1, a 2 multiplied by row 2, and a 2 multiplied by row 3. And I'm going to common factor each of those 2's out. So here comes the 2 from row 1. Then here comes the 2 from row 2. And then here comes the 2 from row 3. Now we have the determinant of A inverse left. There's no 2's left. They're all 3 of them are out. Equals the determinant of the adjoint of A. So the right-hand side is the answer to the question that we're after. Now we need another property. That the determinant of A inverse is 1 over the determinant of A. But we found that the determinant of A is 2, so it's 1 over 2. Now we can plug that in. So we'll have 2 times 2 times 2 times 1 over 2 equals determinant of the adjoint of A. So we get a partial cancellation. 2 times a half is 1, and what's left, 2 times 2, we have 4 equals determinant of the adjoint of A. That's the answer. Now there's a pattern. You could find out what it would be if it was a 4 by 4 or 5 by 5. If all that you knew was its determinant, then there's a nice pattern that comes out. Okay. Number 41. You're given a system of equations, and you're told that the coefficient matrix has determinant A equals -3, and told to use Cramer's rule to find the value of x in the unique solution of the system. So I'm going to write down this matrix. Our coefficient matrix A is 1, 2, 1, 3, 5, 2, 1, 1, 3. And then the right-hand side column vector B is 1, 1, 1. Cramer's rule says that the solution x is equal to the determinant, not the solution vector, just the first component of the solution. X is equal to the determinant of the replacement matrix A1 over the determinant of A. That y is equal to the determinant of A2 over the determinant of A. I'll write down what the replacement matrix is in a moment. And z is the determinant of A3 over the determinant of A. Now it only wants x. It doesn't want anything else. It just wants find the value of x. So we only want this one. We don't need to bother with the other ones. So that's equal to something over, and they give us another piece of information. They tell us that the determinant of A is 3. So I put a 3 down there. Now I need the determinant of the replacement matrix A1. Now A1 is the matrix you get when you replace column 1 with B. A2 is replace column 2 with B. A3 is replace column 3 with B. So here we go. We're going to replace 121 with 111. 352. 113. And now we're going to take the determinant of that. The easiest way to do this is to row reduce. So we take row 1, subtract it from row 2, subtract it from row 3, and then do cofactor expansion, blah, yada yada. Let's get real here. You like the basket weaving. I like the basket weaving. Let's just basket weave. 1, 3 ones. It's nice and calming. It's like a Bob Ross thing to do in math. Happy threes. 5, 1, 1, 2, 3. Okay, and then we hide the last column. And then our determinant is going to be 3 down products minus 3 up products. Downs minus ups. Okay, here we go. Down product, 1 times 5 times 3, we got 15. And another down product, 3 times 1 times 1, plus 3. Another one, 1 times 1 times 2, plus 2. It's a nice number, 20. Now we do the next one. What colors have been neglected so far? I haven't used purple yet. Some purple. Then 1 times 5 times 1, we have 5. 2 times 1 times 1, 2. And then 3 times 1 times 3 plus 9. So that's 20 minus 16. It's nice it's all positive numbers, and you get 4. Hold on, I gotta check something. Something's wrong here. Plus 3 plus 2. And then the up product, 5, 2, and 9. 1, 3, 1, 1, 2, 3. I'm getting 4. Okay, and I should double check everything. So we're looking for the value of x. Alternative is negative 3. Okay, just add that in. So, oops, put the minus there. So our value is minus 4 over 3. Your answer, and that's it. That's the end. Actually, it's not the end. I want to make some more comments about expectations. So I often teach this course, Math 1229, and every year that I've taught it, the same thing happens. Doesn't matter what year, doesn't matter if it's term A, doesn't matter if it's term B. After the exam, everyone always says, that's the hardest Math 1229 exam that I've ever seen. All the other ones are easy. I could do all the other ones without any problems. I could do them all like in my sleep, and I could do two at the same time, one with my left hand, one with my right hand, with my eyes closed. And this one was so hard I could barely do half of it. And this is good students, students who don't do any homework. Like, it's the same. I don't know what causes this. I don't know why everyone always thinks that their exam is the hardest. You're gonna say the same thing. That's I already know that, and I wish you wouldn't. I wish you wouldn't say it's the hardest one you've ever written, but you will. You're gonna say it anyway. It's not meant to be. It never is. But yeah. So this one we just went through. You may say, "Oh, this one was straightforward." Half the students I talked to after this said that they failed it, and they didn't. They didn't fail it, and that it was the hardest exam of the 1229 series that they had, compared to the ones that they practiced from. That they didn't know what was up with it, and it's not particularly hard. It's a normal exam. The exams do tend to be different. You can't rely on the practice exams to tell you exactly what's going to be on your exam. It doesn't work that way. So don't go in with that expectation. Don't go in that your exam is the same thing with different numbers, because it never is. But it's going to bear enough similarities that doing these things is helpful. Good luck.